Hello, my name is Heather. As Vicente mentioned, I'm in my first year of the PhD program at Western University in the philosophy department. And today I'm going to be presenting a paper, presenting a response to a paper by Russell Poldrack, who attempts to provide a philosophical ground for representation learning using artificial neural networks. So Poldrack's main question is, do artificial neural networks form legitimate representations as recognized by a philosophical account? This is an important question to his overarching philosophical project, which I will discuss shortly. And I will respond to his representational explanation of success by comparing it to an alternative approach involving direct perception, which recognizes the important role of constraints in enabling effective action. And then I will end by considering whether his explanation succeeds, as it appeals to the notion that artificial neural networks implement inherent inductive biases. So first, it is important to disambiguate what the term representation means in different contexts. In neuroscience, it is used for a variety of relationships, but particularly indicates a pattern that carries information for various cognitive or behavioral purposes. And Poldrack describes these as systematic empirical relationships that are often found to exist between neural activity and features of the external world. Mental representations are also somewhat of a cluster concept, but importantly appear to have intentional properties. They appear to have meaning and to be about certain things. Common folk concepts include beliefs, desires, and thoughts. Psychology references mental representations, and the computational theory of mind tries to naturalize them, in other words, to offer an account of their role in a cognitive system. So I will use also the term artificial representations to refer to the kind of patterns that an algorithm learns from input data without explicit human engineering of the features relevant to a prediction task. And these will be the focus of this talk. So what is a legitimate representation according to a philosophical account? William Ramsey argues that if we want to naturalize the concept of representation, we can't just use the folk psychological notions because they have features we don't understand in physical terms, such as intentional content. At the same time, we can't just leave them behind, or there would be no point in calling something a representation. So we need a job description for how a representation plays an effective role within a physical system. So meeting this challenge would establish a philosophical ground for what a representation in good standing might be. So Russell Poldrack seeks to establish that neural representations are representations in good standing. And to do this, he argues that artificial neural networks, or ANNs, have been designed to generate artificial representations. Artificial representations are representations in good standing. Artificial representations are relevantly similar to neural representations, and so by transitivity, neural representations are representations in good standing. And as I mentioned, I'll focus my response on his argument for premise 2, that artificial representations are representations in good standing. And I will argue that Poldrack's defense of this premise is inadequate. So Poldrack uses Shay's criteria in his attempt to establish that artificial representations are representations in good standing. Shay provides an elaboration of the conditions that would be required to meet in order to satisfy the job description challenge. He is particularly interested in providing conditions that would support a pluralism about the kind of representational properties, such as correlation or isomorphism, involved in a representational explanation. And Poldrack uses these criteria to give an account of the work of hierarchical convolutional neural networks, or HCNNs, in object detection. And I will briefly introduce HCNNs shortly. But first, the explanandum is object recognition, the system's ability to attribute a label to a specific object in an input image. The second criterion is to offer a putative explanation of A that relies in part on attributing representational properties to the system. So for that, Poldrack offers that the system does representational work by decomposing the visual input into a hierarchy of features that enables object recognition. Criterion C considers how the representational explanation succeeds. Poldrack argues that feature detection is successful since the hierarchical convolutional architecture of the system reflects the, quote, compositional and hierarchical structure of the macroscopic world that gives rise to visual images, end quote. Poldrack calls this an inductive bias, which I'll explain more shortly. And finally, criterion D considers what kind of representational properties enable success. Poldrack describes four. First, reliable stimulation. Second, structural isomorphism of their content with the visual world. Third, that they do the work of reducing the dimensionality of the input. And fourth, that they are decouplable from the triggering stimuli. In a joint paper with Dr. Michael Anderson that we have under review, we argue that Poldrack fails to meet the challenge full stop because the structural isomorphism and decouplability conditions are not met. But here I will focus on the account of success that Poldrack offers in criterion C. So first, let's take a look at an HCNN, or a high-level view. And so first thing to notice is that these are deep networks. They involve a large number of layers. They have a convolutional aspect, which means that these layers perform weighted averages in local regions using a kernel. And this approach has been inspired by biological systems, visual systems, as Poldrack notes. This allows the network to detect features in various locations. It uses nonlinearity like other neural networks to impose a thresholding operation that allows the network to learn nonlinear functions. And it uses pooling layers to perform local reductions of the features generated by convolution. The learning happens in a distinct training phase. An objective function is optimized that quantifies the degree of agreement between the desired classification or output state and the current output using a learning algorithm that changes the values of the parameters. For example, to perform object detection, it transforms the original features of an image into a form that helps to optimally classify whether an image contains a certain object, such as a cat. So Poldrack's account of the success of hierarchical convolutional neural networks, or HCNNs, is rooted in their ability to decompose the input into a hierarchy of features that matches the structure of the world. He claims that the layers contain activation patterns that have interpretable visual features resembling real properties of objects in the world. So here's an example of what he understands as the representations generated by HCNNs. Note that these are not simply a saliency map of the input, but rather a sort of neuron's eye view of the relevant high-level features extracted from previous layers. These visualizations are generated by determining which neurons were most activated in a region and what did they see. So which inputs were most relevant to their activation from the previous layers. But Poldrack isn't only saying that the architecture enables the generation of these putative representations. He's also saying that the architecture functions as an inductive bias. So he asks, how is it that HCNNs are apparently so successful at learning effective approximations in such a relatively short amount of time? An emerging answer to this question is that there is a set of inductive biases that are built into the architecture, which are well matched to the underlying function that relates visual images of objects to their category membership. So is he merely alluding to the assumptions that the engineer has made in building an artificial neural network? Or is he saying that the system is operating as a cognitive system using inductive inference? Well, he ends the paper with a discussion of how representations are universal and necessary for intelligent behavior. And there he concludes that representations provide the organism with an inductive bias that is matched to the structure of the world, without which the organism will be quickly overcome by the curse of dimensionality. So it would seem he is trying to naturalize the kind of representational work that the system does using inductive biases. In fact, in his abstract, he calls them inherent inductive biases of artificial neural network systems. I will have more to say on the legitimacy of this move, but for now, let's consider how the term inductive bias is used in psychology and perception. In psychology, a simple example is that if you point to an object in front of a toddler and call it candy, they will intuitively assume you mean its name is a candy. But the word could refer to any property of the object. Yet humans assume you're naming a class. In perception, Poldrack's claim that HCNNs, or hierarchical convolutional neural networks, are successful by virtue of an inductive bias owes to an indirect view of perception that is common in psychology and cognitive science. The indirect view frames perception as an inferential problem. The features of the input are inherently underspecified for guiding intelligent action. Thus, an inductive bias could lead the learner to favor one action over another. On the other hand, a direct view of perception rejects the idea that representations are necessary to effectively perceive and act in the environment. It holds that effective action and perception co-evolved in perceptual systems such that they are mutually oriented. And organisms in an ecological niche can detect invariance in the flow of information generated by motion at their receptors. So William Warren presents a direct view of perception that's helpful to consider here. He says that the perceptual system need not internally represent an assumption that natural surfaces are regularly textured, that terrestrial objects obey the law of gravitation, or that light comes from above. Rather, these are facts of nature that are responsible for the informational regularities to which perceptual systems adapt, such as texture gradients, declination angles, and illumination gradients. They need not be internally represented as assumptions because the perceptual system need not perform the inverse inferences that require them as premises. The perceptual system simply becomes attuned to the information that, within its niche, reliably specifies the environmental situation and enables the organism to act effectively. So what's important to note here is that these regularities mean that biological systems don't have to be prepared to handle a general space of inputs, but only aspects of their particular niche. So could direct perception explain the success of HCNNs? Well, artificial neural networks also become adapted to a particular kind of data geometry by the training phase that involves an objective or task function, a learning rule, and a training data set. Hassan et al. Argue that the optimization process is akin to the mindless process of evolution, enabling artificial neural networks to perform well within a particular niche. They also emphasize that the structural properties of the problem's embedding space are not the product of the network's architecture alone, but also owe to the objective function, the learning rule, and the training data. The contrast between direct and indirect perception can also be seen as a contrast between function approximation and direct fit. As Poldrack notes, artificial neural networks are very good at function approximation. They succeed because their architecture is deep and includes nonlinear components that allow them to approximate any computable function. However, whereas Poldrack attributes the success of HCNNs to aspects of their architecture that are similar to biological neural networks, Hassan et al. Go further, arguing that they are most like biological neural networks when they use dense sampling for brute force direct fitting of the data to learn its task-relevant structures, rather than trying to idealize the data or track its generative function. So how could direct fit models generalize to new observations if they are constrained by a particular environment or niche? Direct fit models are trained with more parameters than observations. Whereas ideal fit models try to balance the bias variance trade-off in order to generalize. Over-parameterized models avoid the trade-off since they are trained in a rich big data context of observation where it is possible to accommodate the variance of the data with little bias. Hassan et al. Argue that this means big data can turn an extrapolation-based problem into an interpolation-based problem. And interpolation succeeds by mapping local structure, resulting in a model that's constrained to the interpolation zone of the training data, but highly adapted to it. The embedding space is characterized by the density and diversity of the training data. These models make effective predictions while remaining, quote, effectively agnostic to the underlying structure of the world, end quote. Direct fit models generalize without leaving the training environment behind. This contrast can also be seen in various approaches to face recognition. Whereas earlier approaches used a bottleneck layer to further reduce the artificial representations learned from a sparse training set, and this would explicitly define the relevant signal dimensions from the artificial representations, in the hope that these signals constitute sort of general features of faces that can extrapolate to new faces not encountered during training. But on the other hand, the authors of a paper described by Hassan et al. Use a model that directly learns a compact embedding space that corresponds to face identity. So similar faces are separated by small distances in space, and dissimilar faces by larger ones. Because this model is trained with a dense sample of diverse faces, it can achieve very high accuracy on common benchmark data sets. However, if the network was trained with a non-diverse, more restricted training set, it would perform poorly, particularly, for example, if it did not contain certain races. This is because the success of the direct fit approach depends on the sampling and size of the interpolation zone. In other words, the environment constrains the learning. So given these two approaches to object detection with HCNNs, which is best suited to an account of success that is extensible to biological neural networks, since that's what Poldrack is ultimately after? Well, this is an ongoing debate, but I am convinced that dense sampling and brute force direct fitting is ecologically motivated. For instance, we cannot easily predict how an organism would adapt to a new set of constraints because evolution is a blind fitting process that uses a few basic processes to generate great variance. Meanwhile, I'm also not convinced that Poldrack's representational explanation is viable for two reasons. First, I argue that it is more epistemically conservative to account for physical and environmental constraints on the data that generate the regularities the system detects before positing an inductive gap that must be bridged with representational work. Poldrack does acknowledge the role of physical constraints in enabling the success of artificial neural networks by discussing how the space of all possible pixel inputs is constrained by the fundamental physics of the universe. But he pulls in representations to do the job of further reducing the dimensionality of the input without acknowledging environmental constraints. The laws of physics are important, but the environment also constrains the computation. It has particular structural features that generate regularities not described by more general laws, which also mean that the network doesn't have to expect any possible thing. So this means that structural similarity alone offers an impoverished explanation compared to structural similarity conjoined with environmental constraint. Second, since the term inductive bias has a conventional psychological use, if it is to be employed in a functional account of a system's behavior involving subpersonal elements, this would seem to require an adequate response to a parallel job description challenge for the concept of inductive bias itself. So how is the concept of an inductive bias to be rooted in the psychological sense, but also consistent with a scientific account? Ramsey argues that, quote, the concept of representation must in some way be rooted in our ordinary conception of representation. Otherwise, there would be little point in calling a neural or computational state a representation, end quote. But it isn't clear how the roles of informing or denoting serve a physical account of mental or non-mental representation. Similarly, how does the role of an assumption serve a physical account of cognition? So I'm not saying that this challenge couldn't be met, but that he doesn't address it. Also, how does an inductive bias function as something within the cognitive system? Ramsey explains that researchers will often look to non-mental representations, hoping to understand how to naturalize mental representations. He argues that non-mental representations like maps, thermometers, or bits of language have a role to play in informing minds, or else they are not ordinarily considered representations. What we find from non-mental representations is that the concept of representation is invariably tied to a user, who is most naturally understood as a cognitive agent. So the problem is to understand the role that representation plays within a cognitive system without invoking a mind, to understand what representation does to affect inner states of the system. But this is difficult because non-mental representations intuitively function as something external that a cognitive agent uses. Similarly, the concept of an inductive bias is inherently tied to a user whose behavior it affects. And if we want to naturalize it, we need to understand cases where the user is not a full-blown mind, where the user can be a cognitive system and the bias plays some internal role. Finally, what is its content, and how does this content function in the system in a way that is relevant to the effects it produces? Ramsey asks us to consider whether the content of a representation really causes an effect in the system, or does it merely correspond to the effect in a way that just makes sense? For example, if I believe that if P then Q, and also come to believe P, then these two beliefs will cause me to believe Q, though not strictly speaking by virtue of their content. So this is also relevant for the job description of an inductive bias. How does the content of the bias cause the user or system to act in a certain way? Poldrack stipulates that the architecture of an ANN, or an artificial neural network, is an inherent inductive bias. I take him to mean that the convolutional architecture enables learning things like translation invariance, and the hierarchical organization enables learning higher level features. But he doesn't describe how the architecture has content and functions to generate the effect. He does answer how the putative representations generate an effect through dimensionality reduction in answering Shay's criterion D. And he does describe the structural similarity of the architecture to the world. But correlation is not effectuation. The psychological understanding of an inductive bias is that it is a factor that leads someone to favor one action or belief over another when the input is underspecified for a task. Computer science also has a particular understanding of biases that enable various outcomes, and this does include the architecture. For instance, the bottleneck reduction layer that was used in those early approaches to face recognition. But the point is that in order to qualify them as inductive biases in good standing, so to speak, this second challenge needs to be addressed. So in conclusion, convolutional architecture may be biologically motivated, but direct fit learning is also ecologically motivated and well positioned to offer an alternative to a representational account of success. Explaining the success of object detection should at least include both physical and environmental constraints. And more philosophical grounding for the notion of an inductive bias is needed in a subpersonal analysis. Thank you.